Hello everyone. In this video we're going to be integrating a trigonometric function. We have sine x over 1 plus sine x and we're going to integrate this. And I'll be presenting two different methods. And let's start with the first one. So our first method I believe is called Weierstrass substitution. Correct me if I'm wrong. We're going to use a very special type of substitution which actually solves a lot of these integrals. So if you have a rational function of sine and cosine, this method works well in most cases. So here's how it works. We're going to replace tangent x over 2 with z. Of course, this has some implications. And you might be asking, like, where on earth tangent x over 2 comes from, right? We don't have it in the equation. Well, we don't, but we can always get it by using half-angle formulas or double-angle formulas. But let's go ahead and see how or where this leads, right? So if z is equal to that, obviously we can kind of arc tangent both sides, and that gives us arc tangent z equals arc tangent tangent, which is going to be nothing, will give us x over 2. And if you multiply both sides by 2, you get x equals 2 times arc tangent z. This is good. Even though you're not going to need x, you're going to need dx. By the way, I just forgot to include it here. Have you noticed? So let's go ahead and add dx here. Normally, if you're integrating something, you have to have a dx. Just like when you differentiate, you have dy over dx, right? Anyways, you get the idea. Hopefully, you guessed it. Now, we don't need x, but we do need dx. So to find dx, we're going to go ahead and differentiate both sides here. Obviously, you know the drill, hopefully. And to differentiate arc tangent, you got to remember the formula. It's 1 over 1 plus z squared. It's a very special formula, and you can actually use the inverse function identity or formula to prove it. Fairly easy. It comes from the fact that 1 plus tangent squared is secant squared, which happens to be, by the way, secant squared is the derivative of tangent. Anyways, you can go ahead and try to prove it. It's fun. From here, dx becomes 2 times the derivative of 1 over 1 plus z squared, which is the derivative of arctangent, multiplied by dz. Of course, we're going to write it in a more compact form as 2 dz divided by 1 plus z squared. Okay? So this is dx. We don't need x like I said earlier. And this is z. In case you end up with something like tangent x over 2, you can replace it with z. I don't think you're going to need x over 2 because you don't need x. Now, here's the fun part. What is sine x, right? That will be the question. And since we do know that tangent x over 2 is equal to z, that's what we used, right? We can go ahead and actually use the double formula. What is tangent x? X is 2 times x over 2. So if you remember the formula for tangent to alpha, you can actually use it as 2 times tangent alpha, which is x over 2, divided by 1 minus tangent squared alpha. Okay? So that's the next thing we're going to use. Wait a minute. That gives us tangent. It doesn't give us cosine or sine. No worries. Once you find tangent, we can also find the others, right? So if you replace, in this equation, if you replace tangent x over 2 with z, remember that that's z, you get 2z, or not 2z, right? That's the problem, divided by 1 minus z squared. So that's another identity you're going to need. That's tangent. We don't have tangent x in our equation, so that's fine. But we can actually go ahead and find sine and cosine from here. How? Trigonometrically or geometrically or mathematically, however you want to do it. We're going to draw a right triangle. This is going to be x now. And now we're going to place the opposite side and the adjacent side. And let me tell you, without further ado, that the hypotenuse is going to be 1 plus z squared. If you just do the Pythagorean theorem, that's what you're going to get. So from here, you can find sine and cosine. But do I need cosine? Nope. I only need sine. So let's go ahead and find sine x from here. Remember, that's opposite over hypotenuse, right? That is 2z over 1 plus z squared. Great. So we got everything we need. We have sine x and we have dx. That's all you need, basically, right? But to be able to find it, we kind of had to go through several loops, right? So now, here's what we're looking at. Sine x over 1 plus sine x dx. Now we're going to go ahead and replace sine x with 2z over 1 plus z squared. And then denominator, the same thing. Of course, you'll make a common denominator and simplify. Here's the critical part. You have to replace dx with something. And ta-da, we already have it, right? Dx is, oops, this is probably better, 2 dz over 1 plus z squared. 2 dz over 1 plus z squared. Awesome. Now, this is really cool because obviously 1 plus z squared is going to cancel out. But let's go ahead and simplify this first. We're going to get 2z over 1 plus z squared. If you make a common denominator, you're going to get z squared here. Z squared plus 1 plus 2z divided by 1 plus z squared. But of course, you have to flip and multiply it. And notice that the denominator just becomes z plus 1 quantity squared. I don't know if you want to do it that way. And then, of course, don't forget to multiply by 2 dz over 1 plus z squared. Now, let's go ahead and move this stuff over here without hopefully hurting. Oops, didn't work. But anyways, we're going to go ahead and erase that piece, which we don't need anymore. Now, this is going to be, oops, this is going to be integrated, okay? Now, let's see what cancels out. These two things cancel out, and then nothing else. That's it, right? So from here, we're going to get 4z in the numerator, and the denominator is going to give us z plus 1 squared multiplied by 1 plus z squared. You can also write it as z squared plus 1 if you want to stick to the standard form of a polynomial. And of course, do not forget dz. Otherwise, you'll get dz, right? Okay, now, where do we go from here? This looks like partial fractions, doesn't it? We're going to go ahead and split it up into pieces. And I may or may not do the whole thing because I'm lazy and this is too much work. But, you know, you can let Wolfram Alpha do it for you or some type of LLM, AI, whatever you want to call it. So you can basically do the following. We're going to look at the main parent function, in other words. So here we have z plus 1. So that's linear. We have to write it as a over z plus 1. Because the difference of degree must be 1 between the numerator and the denominator. So if your denominator is linear, your numerator must be constant. Make sense? But you're not going to stop at that because we have the second power. We kind of have to build it. So we're going to write the next thing. Again with a constant because the parent function is linear. B over z plus 1 quantity squared. And then for this one, since it's not factorable, and by the way, you could also do the same thing. You're like, pretend it's not factorable. But it's better to do it that way, I guess. This is going to be like cz plus d over z squared plus 1. Why? Because in the real world, we cannot split this up. And we do need a linear because the denominator is quadratic. Make sense? So from here, it's going to be lots of fun. You're going to make a common denominator, find a, b, c, d. And then that'll give you a split. That way you can just integrate everything separately. Obviously, for this one, you're going to get something like 1 over z plus 1, because if you think about how to integrate 1 over z squared dz, it's going to be negative 1 over z. And this comes from the fact that if you differentiate 1 over z with respect to z, you get negative 1 over z squared, right? The power rule. But if you memorize the formula, it's a lot better because you're going to see this a lot. For this one, this is just an ln. And for this one, who knows? Depending on the values of z and d, c and d, you may have to split it up, but piece of that will probably be some type of arctangent. May not be, depending on how this comes out, okay? Because imagine you had this is perfectly ln, right? Because u sub. All right, hopefully you get the idea. And from here, you can hopefully proceed and let me know what you find. And then you have to back substitute. That's a lot of work. That's why I leave it for you as an exercise. Don't hate me for that. By the way, I made a video yesterday. I don't know if you noticed, actually 2 days ago. Yesterday it was shorts. 2 days ago, it was a video response to Black Pen, Red Pen. I also shared the post with you. You can go ahead and check it out. Anyways, I'm not going to get into the details. You can all go ahead and read that. Second method is actually pretty interesting, but again, it's up to you to decide. This method does not always work nicely, but in this case, it does. So here's how it works. Notice that we have a 1 plus sine x, or we could have had 1 plus cosine x. That's really cool, because what we can do now is take this and use a conjugate. Conjugate means kind of like if you have a plus b, you have a minus b. A plus bi, a minus bi. Wait a minute, what is a plus bi? A plus bi is another channel that I have. It's all about complex numbers goals, so go ahead and check it out. Commercial break. Okay, let's continue now. We're going to multiply by 1 minus sine x and divide by that. So we're essentially multiplying by 1. But now we have sine x minus sine squared x in the numerator. In the denominator, we have 1 minus sine squared. Obviously, Pythagorean theorem tells us 1 minus sine squared is cosine squared, because sine squared plus cosine squared is equal to 1. You should definitely know that. It's a super duper important identity after, I would say, difference of two squares and this one. They are super duper important. Now, our integral kind of turned into something like this. What is so good about it, right? You might be asking. Okay, well, here's what I'm going to say. First of all, oops, I forgot to replace it. 1 minus sine squared is going to be replaced with cosine squared. And guess what we can do now? We have a single thing in the denominator, so we can split it, right? Kind of unsubtract two fractions. So we can kind of write it like sine x over cosine squared x dx, and then minus sine squared x divided by cosine squared x dx. Awesome. What about this? Well, we're going to split it up. Okay, again, you can do this in two ways if you want. So if this is the second method, one of them is going to be 2a, the other one is going to be 2b or not 2b. So we can do it like this. Cosine x, we can set it equal to u. And then negative sine x dx would be du. So sine x dx would be negative du. Okay, you get the idea? So we get something like negative du over u squared. Make sense? And of course, like we just talked about it, right? Negative 1 over u squared, its integral is 1 over u, right? So this is going to be 1 over cosine x, which is secant. If you don't want to do that, perfectly fine, understandable. You can do this. You can split it up into two pieces, sine x over cosine x times 1 over cosine x. Let's go ahead and deal with this integral first, and then we'll do the second one, because the second one is actually fairly easy. This one is going to be like, what is this? Sine over cosine. You must know this, right? Tangent x. What is this? Secant x. Well, I want to write the secant before the tangent because it just looks better. And then, guess what this is? Secant x tangent x. Didn't you memorize this when you were taking calculus? If you didn't take calculus, don't worry about it, because I have a bunch of videos. Go ahead and check them out. The playlist, calculus, and lots of integrals. Differential equations too, by the way. But secant x tangent x is the derivative of secant. So this is secant x plus a constant. I'm going to write the constant last, but I'm just telling you so that we're mathematically correct. So that's it. But if you use the u sub, you would also get the exact same thing, because 1 over u is going to be secant x. Does that make sense? Now, what is this? This is tangent squared. Uh-oh. How do you integrate tangent squared? Let me show you. Easy. If you kind of try to do some crazy stuff like u sub or what else can we do? Sine squared over cosine squared. Yes, you can do this. Sine squared can actually be written as 1 minus cosine squared. Then you can split it up. There's no need, because here's the nice trick, that really cool trick that works all the time. I'm going to add 1 to tangent squared and subtract 1. And guess what happens? Tangent squared 1, tangent squared x plus 1 is secant squared. So we can kind of split it up into two integrals. Secant squared x dx minus 1 dx. Well, secant squared is the derivative of what? Remember I told you before, tangent. So this is tangent x, this is minus x, and then some constant, whatever. Let's go ahead and put it all together, so that way we can get the total answer. What was the first part? We got secant x from there. So it's going to be secant x, and then we have tangent x, and then minus x plus a constant. Now, what was this? We were integrating what? We were integrating sine x over 1 plus sine x. Let's not forget dx, so that this is what we get basically. So by splitting it up into two pieces like this, by using a little quick trick of conjugates, you basically get like two integrals that are very easy to evaluate. Okay, the first part is, what was that again? Did I mix them up? I think I mixed something up. Okay, let me double check. No, actually, the integral of tangent squared is secant squared minus 1. Okay, yeah, that seems to be correct to me, I think. Anyways, let's move this a little bit. So that should be the answer. And this brings us to the end of this video. Well, thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.